This is the first video in a series of lessons that we'll do on construction of steel within the industry. And to begin with, we want to start looking at the properties of steel. Now, we've done this a little bit already. When we went through Chapter 5, we talked about some material properties. And so this video will include a little bit of review on that. I've got here on the screen just a handful of things already pre-drawn out. Talking about steel properties here, there are some properties of steel that are constant and some that vary. And one of the things that remains constant is the density or the unit weight of steel. So we'll go ahead and write unit weight in here. How much the steel actually weighs per cubic foot, for lack of a better way to put it. That remains constant. And another thing that remains constant is the actual stiffness of the material. And by stiffness, we're talking about the material stiffness here. And so that would be the modulus of elasticity E that we're used to seeing here. I'm going to highlight stiffness because that becomes one of the key properties that we want to capitalize. Now, one of the things that varies with steel is the strength. Again, we'll grab that and highlight that because that's an important property we want to deal with. Also, the hardness of steel can vary. It's related to the strength. I won't focus too much on that, but just another property to note there. If you recall, when we were looking at steel materials, there tends to be a sort of linear portion of the curve right here. So if we're looking at the stress-strain curve, if we load it up to a certain height or a certain stress value, that there will be some sort of motion. By motion, I mean compression, strain, movement that occurs. And then we hit some sort of a general yield point, and the steel kind of comes down and comes back up just a little bit. And generally speaking, this is I'm not going to exaggerate the curve quite as much today, but this represents ordinary structural steel. Now, there's two different basic strengths that we utilize. That's an E. Two different strengths that we utilize for our ordinary structural steel. And these represent the actual strength of the steel. We talked about that strength that varies right there. So 36 KSI steel, sometimes called A36 steel, is one of those. The other one is, would be a little bit higher up, but 50 KSI steel also represents another value here. And what I want you to notice here is if we go to 50 KSI steel, the modulus of elasticity remains generally the same. So we follow that same linear portion up, but the yield strength is a little bit higher. Follows the same sort of curve. Note that it doesn't quite have the same ductility, meaning it doesn't have the same strain capacity. But those are our two basic types of structural steel. There's other kinds of steel that exist. Usually we don't see them too much in the construction industry as far as what we build with. Sorry, that's a little sloppy line there. Higher strength steel. Again, notice the ductility is being sacrificed to get the higher strength. And every once in a while you'll see a structure that's made out of high strength steel. Usually skyscrapers, things like that, tend to start utilizing slightly higher strengths, get higher capacities without as much weight. And then steel can actually even go stronger than that. I'm not going to keep this to scale right through here. But we get up into what we call the super strength steels. So this would be high strength. This one up here would be super strength. And when we start getting into like construction equipment, things like that, these are the types of materials that they can actually get as high as 250 KSI. When a material like this decides to break, they're very brittle, they're very dramatic, and it's very sudden. But they're very, very strong, and you gain a very high strength with a significantly lower mass of steel when you're using this. One quick thing to note about this diagram, the modulus of elasticity, the slope of that line, if you recall, the slope of this line right here is the E value, the rise over the run, the stress over the strain value there. You can look that value up. Tends to be on the order of 29,000 KSI is what's shown in the textbook. But the actual elastic range will vary depending on the strength of the steel, meaning how much strain actually occurs for the steel being utilized. Now, I want to quickly talk about beam properties as well while we're here on this topic. So let's start with a couple general principles here. The most common beam type when we're dealing with steel is the wide flange shape. First off, if you're not familiar with that term, let's reacquaint you with it. A wide flange shape looks like this, sometimes called an I-beam, but there are some minor differences between a wide flange beam and an I-beam and a wide flange beam. Why is this the most common type? Let you think about that just for a second. Have you formulated an answer? With steel, steel is significantly heavy and significantly expensive. And so what we're trying to do is capitalize on the most efficient shape that we possibly can with the amount of material that we're using. And therefore, the wide flange shape is the most common. Now, you'll often see the designation for a wide flange shape, something like this. For example, you'd see W12 by 26. This would be a specific type of wide flange beam. W for wide flange. The 12, on the other hand, has to do with the nominal depth. So for this particular shape, the nominal depth would be approximately 12 inches tall. It might be 11.9, it might be 12.1, but it's going to be very, very close to 12. The 26, on the other hand, is how much the beam weighs. So this particular section would weigh 26 pounds per linear foot. If you were to cut a 1 foot piece off this beam, just a 1 foot chunk of a W12 by 26, and you put it on a scale, it would weigh 26 pounds. Now, when we're dealing with steel sections, we're trying to decide which ones to use. A good rule of thumb is this. When you're selecting which wide flange shape to use, you're looking at a big table and you've got a whole bunch of different options, ones that will work. The most common approach is simply to use the least weight selection. Because steel typically costs a certain amount per pound, if you go with the least weight selection, then you're typically considered, most economical. Now, there are some factors that sometimes get into this, also get considered. And one of those that we would want to think about is the dimensions. Occasionally, the cheapest selection might be a 14-inch tall beam, but you've only got 12 inches to work with. And so you might go with a slightly heavier one there because the dimensions matter. Generally speaking, though, at least for the sake of this class, anytime we give a homework problem, I want you to run with the least weight selection as your answer.